My name is Logan Saether. I'm a Solidity developer at Chronologic. We've been working on the Ethereum alarm clock, which is a protocol for scheduling transactions and having those transactions later executed in a decentralized, trustless, on-chain way. So I'll be giving an overview of how that protocol works and going into the history of the alarm clock and what we've been doing with it. So the alarm clock is an open source smart contract protocol. It was created by a developer named Piper Merriam in 2015. It was one of the first large-scale decentralized applications built on Ethereum. Piper is now at the Ethereum Foundation, working on Pi EVM. So the alarm clock kind of fell into a state of disarray, and it wasn't maintained and wasn't working for a while. So Chronologic came in toward the end of last year, got it functional again, got it working, and we started building a dApp to make it a lot easier to use, and we're currently working on a version 2. So we have it on the Coven testnet. We're right now waiting for a security audit, and we're going to put it on the mainnet and want developers to start getting their hands dirty with it. So Piper Merriam giving the talk on the Ethereum alarm clock at the first DevCon. We just finished giving another talk at the conference in Paris, ETHCC. So it's something that's been around for a while. So what's the problem that the Ethereum alarm clock is trying to solve? The problem is there's no native way to schedule a transaction and have that transaction executed at a later point. This is because all transactions are executed instantly. There's been solutions somewhat with cron jobs, having things run on servers, setting times to send executions, but everything is kind of just a hacky way to do it. And what the alarm clock tries to solve is a kind of global solution that runs on the blockchain. And I'll go into how exactly we make that a decentralized protocol. So what are the use cases? Why do we want to schedule transactions? Well, there's a ton of use cases, actually. So tokens from ICO contracts, when ICOs launch, they, depending on time zones, they can be either late at night, maybe you're at work, whatever it is, maybe you don't want to be at the computer. So you could schedule a transaction. That transaction will buy the tokens for you. We have a lot of things like recurring payments, which right now can't really be done. With the alarm clock, we can schedule those and have those go through on time. Wallet integrations, Ethereum name system reveals. So right now the ENS is a two-step process. You commit, and then you later reveal that commit. With the alarm clock, we can turn that into a one-step process where you commit and schedule the reveal at the same time. So you don't have to worry about coming back to your computer 2 days later. And then running a time node, which is, these are the executioning clients on the protocol, and they're similar to miners, and I'll go into how those work, but they're essentially the counterparty to the scheduling half of this. So this is an exciting partnership we're announcing with MyCrypto. They recently just released their beta wallet, and we are currently building a pull request. And we've been talking to them, and we are going to make the Ethereum alarm clock integrated into the MyCrypto wallet. So these slides are from ETHCC, so if you see things about the booth, that's why. But right now I'm going to go into kind of a deep dive. Just so I know the audience, do we have many developers here? Raise your hand if you're a developer. Okay, cool. So it's a good portion of developers. So yeah, so I'll kind of break down the Ethereum alarm clock contracts and show you guys how that works. This is just to illustrate that the two types of accounts on Ethereum. We have users who control private keys. These are the ways that these are the accounts that actually send and sign transactions. And then we have smart contracts, which aren't controlled by a private key and don't have a way to publish transactions to the network. So what the Ethereum alarm clock does is allow the smart contracts to become executable and wake up on their own. So I'll go through kind of how this process works on a high level. So on the left-hand side, we have a user who knows the transaction they want to schedule. So they'll submit this information to the alarm clock protocol. The alarm clock will deploy a new smart contract onto the blockchain. On the left-hand side, we have time nodes, which are these off-chain clients, which are watching for each new smart contract. And they'll store these and perform certain actions on them depending on at what state these transactions are at. So they'll either claim these transactions or execute these transactions. And when they execute transactions, they'll get paid a bounty. Here's like the smart contract architecture. We can break it up into 4 major pieces: the schedulers, the request tracker, the Requestfactory, and the transaction requests. This is just to illustrate that the schedulers are the top-level API of the whole thing. And so here's the dependency chart. What we have is about 20 contracts. We don't even have all of them pictured here. And they all rely on each other for the various logic. And these are all separate contracts deployed on chain and talking to each other. So it's a pretty involved protocol from a technical standpoint. So I'll go into how a transaction is actually scheduled into the smart contracts. So like I said, this is the top level entry point. Here's part of the interface here. I just want to point out the parameters that someone will send to schedule a transaction. So of course the recipient, which is the destination this transaction will be sent to. Some call data. So this is in the cases of scheduling a transaction to a smart contract. You can encode the data beforehand to trigger a function. And then we have a few integers, which I'll go into right here. So if anyone's familiar with Ethereum transactions, the first 5 are just the parameters you need to send. So the gas you're sending, the value. Actually the window starts, so this is when the transaction will come up to be executed. The window size, so the length of that execution window. We have the window start, the gas price, a few parameters which are protocol specific. So we have a fee, which is this optional way for wallet integrations to kind of make a passive income. So for example, the MyCrypto integration, they'll be setting a fee from the front end, like from the JavaScript, not from the smart contracts portion. And they'll be sending that fee to themselves anytime someone uses the MyCrypto integration. The bounty is a way that we've incentivized the time nodes to execute transactions. And then the required deposit is a value that the time node sends to claim transactions. So the Requestfactory is like a lower level smart contract. It does some cool stuff on the back end. We recently just got the gas down and optimized it from 2.5 million to 1 million thanks to this GitHub repo here, which essentially makes it, when it deploys new contracts, it deploys a very small contract that kind of proxies calls. So I'll walk through here. These are just the interface. If you're curious, you can look through that later. So the scheduled transactions or the transaction requests, each one is its own contract. Here's the interface for that. It just contains logic to execute that transaction, claim it, proxy. So we have this situation if this transaction is buying tokens from an ICO contract, it becomes the owner of those tokens. The solution is after that transaction is executed, the owner can call proxy and send those tokens out. And then we just have a few getters there. So proxy, that's a really cool thing. You might want to look into that later if you're a developer and you're curious about building smart contracts. But now I'll talk about the execution flow. So that's the way that scheduling works. On the other end of the protocol, we have these people running time nodes. And these are the people that actually execute the transaction when the execution window begins. Yeah, let's go through that. All right, so the time nodes, I'll give you guys a demo of a couple things we've built there, but they're essentially just clients that are running, and they will send transactions. They'll ping the smart contract, and that will launch the transaction when the window begins. The idea is that we want people to run these, so we schedule a bounty into each transaction. So when a time node executes a transaction, they'll get paid back this bounty, as well as the gas. So theoretically, this is always profitable to run one of these clients. We've been trying to make it easier for people to just get up and started doing this. We want a lot of these because if, let's say I'm running a client, you want a transaction to be executed on time. There's only the guarantee that I'll do it if I'm the only one running the client. But if I'm doing it and someone else is doing it and a lot of other people are doing it, we now have all of these clients trying to compete with each other for this bounty. And this is a way that we're trying to decentralize this server structure here. So this is how we do it. And this is what overall makes the protocol crypto economically sound, is that there's real incentive for people to be running these time nodes and for them to be executing transactions on time. So we've also been building JavaScript tools. So developers, we've been trying to make it really easy to use these contracts in your dApps. And to use the Ethereum alarm clock from the command line. Let's see. I can give a demo if anyone wants to see that. Yeah, cool. So this is the first execution client we built at Chronologic. It's pretty rough. It was pretty rough around the edges, and I'll show you guys the dApp we've been building as well. So this is a command line tool. You need to be running a full node to use this client. All right, let's go there. Sorry, my typos. I don't usually use Windows, so I SSH'd into a AWS instance for this demo. Anyway, so you have to run a full node, so that's what we're doing here. You can download our tool from NPM. It's called eac.js. And the way to use it is like this. So the S here means schedule, and there's two varieties of scheduling, one with block times or block numbers and one with timestamps. So right here we're just saying, let's start the scheduling wizard using the block numbers. And then it'll walk us through the parameters that we schedule in. So for this, I'll just go through the defaults. It'll ask us to confirm. And then, so we're actually sending a transaction to the Coven test network here. And it mined the transaction, it's successful. If we want to check, we can use the transaction hash here. Oops. And we see that this transaction deployed a new contract and sent the funds to cover this, this execution. So that's cool. And we can also execute that transaction now from the same tool. So using eac.js, we can pass in C to run the client. It uses an unlocked account from the full node that we're running to execute. Oops. I'll start that. It stores a cache of all the transactions, so I'll go ahead and dump that out there. And we see that we have the address of this scheduled transaction, as well as the the execution window start. So it might take a few minutes to actually execute this transaction, but we'll come back to this. And I'll show you guys okay. I'll show you guys what we built after that, because we didn't want to make everyone use the command line. So we built a DApp, a front-end interface to the same thing. So instead of having to input all of that into the command line wizard, you can go to app.chronologic.network and do it using this nice interface instead. So yeah, this is currently on Kovan. It requires MetaMask. Do you guys know MetaMask? So MetaMask is a browser wallet that lets you send transactions to the blockchain really easily. It's giving me some trouble here, so maybe I won't actually send a transaction, but I'll go ahead and walk you guys through how much easier this is. So we have the scheduling portion of that. We have something similar to Etherscan where you can see all of the scheduled transactions in a scanner. And then we actually let you also run a time node in the browser. So I'm not connected to the test network right now here. But yeah, so you can actually execute transactions by leaving this open in a browser window. And all of that is open source. So if anyone wants to look at that, it's available on either the Ethereum alarm clock GitHub repository or on the Chronologic GitHub repository. And now let's see if this transaction was executed. I'll go ahead and dump the cache there. And we have a 99, which is the code that means that was executed. So just to check, let's put that address into Etherscan. And we see a minute ago a transaction was sent. And we see the transfers here, which are sending the different values, the bounty to the time node that executed it, as well as sending the actual transaction that was scheduled. So yeah, so that's how it works from a client perspective. You don't really need to do anything. You just either leave that open on the command line or leave that open in a browser window. And it'll, if people are scheduling transactions, it'll execute them. And so, yeah, so that's about it, really. Oops. Yeah, that's about it. So, cool. So what are we planning for the future? So we just finished getting it working again. We're calling this version 1. We know it's not optimal right now. It actually costs a lot of gas to schedule transactions. So we were talking with a lot of people and a lot of projects at ETHCC just last week, and we've come up with a lot of interesting ideas to make this more optimized. So what we're looking at right now is possibly state channels, which are this really interesting concept of being able to do a lot of things off-chain and then submitting that back onto the blockchain in a way to prove what happened during this time. And we're also considering other things like stateless, using IPFS. So instead of putting everything on-chain, we can store things in IPFS. And we have a token called the day token. And we're not currently using the day token with the alarm clock. To use the browser time node, we require a certain amount of day token, but we're looking at ways to use the day token in interesting ways with the claiming mechanism. So that's another thing that we're researching, and overall we're pushing this all forward into a version 2. So yeah, that's about it. So if anyone has any questions, I can answer them.
Well, I have a question. So what's the overhead on top of the gas required by my function? What's the overhead, for the schedule?
Yeah, great question. So when you schedule transactions, you pay the gas up front. You also pay the bounty that will get rewarded to the time node. And then you also pay the fee if the fee is if you're using like a front end that has a fee implemented. So that's the overhead.
So did you calculate what's that roughly? Is it?
So interestingly, both of those are kind of like user input there. So it's like you can set a small bounty if no one's really scheduling and you're pretty sure a time node will pick it up. If the network's filled, you'd want to set a larger bounty. And the fee is dependent on what interface you're using there. So
with bounties, is it like with mining? So the executors can select the ones with the higher bounty?
Mm-hmm. So the client will look at what has the highest bounty and execute those first. Cool. All right. Thanks a lot.